Alright, in this video I'm going to talk about finding natural frequencies of a shaft using Rayleigh equation. So here's the equation for natural frequency or first critical speed of a shaft when there are uh, like machine elements sitting on that shaft. Those could be for example like gears. Alright, so for this I'm gonna do this problem from Shikley's book. Let's review this problem. Um, this problem, we have a shaft which has a total length of 31 inch. It's sitting on two bearings, left and right, and there are two gears on this shaft. One of them is 35 pound from the left bearing, 7 inch from the left bearing, and then there is another one, another gear sitting on you know, 11 inch from the right bearing. The weight of that one is 55 pound. So we want to find first natural frequencies of this shaft using this equation. Alright, so for this, let's look at this equation, see what these are. So what these variables are, what you see here. So first natural frequency of this shaft could be calculated using this equation. So in this equation, G is gravitational acceleration, and then W or omegas are the weight of the machine elements sitting on the shaft, and then Y is the deflection of the shaft where that machine element sits. Okay, so for this, let me explain it here based on this shaft. So in this shaft, we have two omegas or two W's, you know. W1 is the first gear, 35 pound, and the other one is 55 pound, W2. So Y1 is due to the weight of these two gears. This shaft is going to deflect, is going to deform, right? So Y1 is the formation of the shaft where the first gear sits, and then Y2 is the deformation of the shaft where the second gear sits. So Y2. So if I have those, if somehow I calculate those Y1 and Y2, they're gonna go to this formula, and then we can find first natural frequency, and it's gonna be in a radian per second. Alright, so as you see, the key variable here that we need to calculate to find the natural frequency is the y's. We need to find the y's. So at first, I'm going to show you guys how we could use ANSYS actually to find these y's, these deformations. So let's look at this problem again, see what other information we need. This shaft has length of 31 inch, the diameter is 1 inch, and the material is steel. So but mass of elasticity of 30,000 KSI. So these are the information we need to model this. So at first I'm going to use ANSYS APDL to find these deformations Y1 and Y2, and then I'm going to talk about the two other methods that we can use to find these deformations. One of them is based on superposition, using superposition tables, and another one, you see this one, I took the relevant case from superposition tables, and the other one is based on influence coefficients, which is basically, again, same thing, is based on superposition, but this influence coefficient method is a systematic way of using superposition table. So I'm going to explain that too at the end. This is what Shigley book uses for this problem. So, alright, so let's do it. First, as I said, I'm going to use ANSYS APDL. I have it already opened here. So, ANSYS APDL is open. By the way, I forgot to say, you know what, if you guys want, you can all use actually the ANSYS directly and find natural frequency. You can model this shaft and find natural frequencies directly from ANSYS, but that one I have it covered in another video. So, but here I just want to use ANSYS to find those deformations and then use Rayleigh equation to find natural frequency. So let's do it. Alright, so I open the ANSYS APDL. I go here, preferences. We're going to say to ANSYS that we're going to do a structural analysis. Alright, and then I go here, pre-processing. I'm going to specify my element type as beam element. So we're going to use beam element with 2 nodes. So beam 188 is the name of this beam 188. Going to use that here. Alright, so then we're going to specify the material, define the material. So I go material models, then structural, linear, elastic, isotropic. So my material is steel. Modulus of elasticity for steel is 30,000 KSI. But I want to do my calculations in PSI. So I'm going to do here 30,000 instead of 30,000. I'm going to put 30 million. Alright, and then Poisson ratio is 0.3. I close it. There you go. Then come here, sections. We have to specify the section here. So then common section, you go here. Our circular section is a circular section, or a section of the shaft is circular. And then the radius is, diameter is 1, so radius is going to be 0.5. If you guys want, you can preview this section and see what the moments of inertia and other properties you may be interested. So you see the moment of inertia we're going to need is this guy, Iy, and also Izz, Iyy or Izz. See 0.048986. It's what ANSYS has calculated. If you notice, Shigley's book is slightly off from here. With this number we have here, it's not big, but there's a slight difference. So let me go here and show it to you guys. So Shigley's book is calculating that to be 0.04909, which is slightly off. So let's calculate it ourselves. So 1 divided by 64 times pi. Let's see who is right. Yeah, 49087. Alright, so it looks like Shigley's book is more accurate on this. This is a small rounding problem. I think ANSYS has probably used numerical methods to find moment of inertia. That's why you see this difference. But this is not going to cause a big issue for us. Alright, so alright, then let's go model the shaft. Okay, so next thing is I'm going to define key points for my design. By the way, let's look at the shaft again. There are some key points here that are important for our model. Those key points are this. First bearing on the left, I'm going to consider that point 1. Then this gear, I'm going to consider this point 2 key point, and then point 3, and then last point. the right bearing. So I'm going to define them like that, and so let's do it. So 0.1, 0, 0, 0. Okay, so that's 0.1. Then 0.2 was the first gear located 7 inches from the left. So let's look at them. So this is 0.2, and then 0.3 was okay, 20. Okay, let's look at it, see what 0.3, well, how far was located from the left. So 13 and 7 will be 20, right? So 20 inches from the left is a 0.3, and then 0.4 was 31 inches from the left. There you go. So then I'm going to connect these key points through a line, a line. So go here, create lines, and then lines, a straight line, go 1 to 2, 2 to 3, 3 to 4. So now I have 3 lines. So go here, these are my lines. If you like, you can have them, you can have them look at the list. So list of the lines that I have. Yeah, we have 3 lines. You see how the key points are connecting our key points. So next, I'm gonna need to mesh this model, right? Okay, so how do I mesh? I have 3 lines. I know I'm gonna mesh them. So we are doing the formation analysis. So I'm gonna break each line into 5 elements. I think 5 is sufficient. If you guys want, you can do sensitivity analysis. Do 5 elements, then you can do more, and then see how much results change. Or you can start from 1 element and then, keep adding more. And then you see if your results get converged. Right, so I'm going to do 5. 5 is going to work. So size, control, here, manual size. I'm going to go all lines. I'm going to have each line. You see in this window, I'm going to say number of divisions, element divisions. I'm going to say all lines have, let's say, 5 elements on them. Right, so then the size is decided, and then we mesh it now. Lines, all lines, they are meshed. Then you go to loads, analysis types, is a static, and then apply structural, displacement, and key points. Okay, this key point is the left bearing. At that point, translational motions, I'm gonna fix it. Rotation about X is like torsion, is like twisting, so I'm gonna close that. But about Y-axis and Z-axis, I'm gonna let that to get sloped. You see what I'm saying? I let that to have slope. I will let slope happen. So everything else, I'm gonna zero it. Alright, so then this is it. And the right one, usually bearings, one side is fixed, the other side is floating. So on that right side, I can actually say X has freedom, in X direction. I'm not gonna zero that one. And then Y and Z, I'm gonna fix those. And rotation, again, you can say rotation about X is 0, but the other ones I let them be free. Okay, so this is our bearings. And then I need to apply forces, right? So go force on key points I'm gonna apply. And if you guys like, you can go here and plot the key points. So Yeah, these are my key points. If you want, you can see the numbering too. So key point numbers, let's show them. Yeah, see, number 2 was my left bearing, left gear, and then number 3 was my right gear. So on number 2, my force, if I consider weight, is gonna go against y-axis. So go here, say Fy, and I'm gonna put negative. That one was 35 pound going down, right? And then for number 3, I have again force going down, this time 55. So okay, there you go. So we have our model made. So now next I'm gonna solve it. So let's go here and say solve current thing model, and then done. Alright, so let me see. So my solution is done. Make sure that everything is going well. Okay. Alright, so then solution is done. Let's look at the numbers. Okay, so I come here, then general post-processing, go list results, nodal solutions. I want to see degrees of freedom solution. I want to see displacements in y direction, deformation in y direction, right, y-axis. So then okay, these are my numbers. Alright, so you see all displacement on different nodes, but what I want is the solution. We have to look at it on where the the first gear and second gears are. So let's see, by the way, where those are. That node, those key points. Let me, by the way, come here and find which node is on key point 2 and key point 3. So I want to see that. So come here, properties. No, go here. Okay, where was it? It should be here. List. Yeah, nodes and attributes. Coordinates. Let's see, where was it? Okay, so elements. Oh yeah, we can see it probably here. Yeah, no, not this one. Coordinate, nodes, properties, results, others. Yeah, okay, let's see what they are. I see elements. Okay, nodes. Oh, okay, from here we can figure that out actually. If you remember, it says node 2. Node 2 is located at 7" from the left. So that's actually where the key point 2 was. So that's where our left gear is. And then if you look, the right gear was located at point 3. That one 20 inches from the left. So if you look at here down, you see that's node number 7. So this is these are the nodes I need to look at for my deformations, right? At number 7, node number 7, and node number 2, right? We're gonna see the formations. Alright, so now go here again. Let's look at it. Node number 2, this is the deformation. So let's see if I can take them out. Let's see if I can copy paste it, Control C. Let's see how they compare to the what you had from the book. Alright, so number 2, 0.019489. So see how much book was claiming. So the book, I'm going to explain this later, finds the y1, the formation at point 1, to be 0.019445. So it's very close, right? So this is what we have. This guy, this one. And then the other one, number 7, you have 0.02724. 0.02724 what I have there, but here is 0.02722. So it's very, very close. Alright, so this is how we could use ANSYS to find those deformations, and then next would be use these to find the natural frequency. So let me do that. So you know what, I'm gonna, let me see, I erase this, erase the rest, what I don't need, and then these guys eliminate. Okay, so this is y1, this is y2. Okay, now see if we can make it large. Alright, y1, y2, and then now let's use this Rayleigh equation and then find the natural frequency. So first, natural frequency. Alright, don't need the answers now, so let me close this guy. Alright, then come here and find our natural frequencies. I'm going to use this guy, this equation. Yeah, alright, let's use this equation. So omega 1 see if I can make my iPad working. Can I write down anything here? Alright, so omega 1 equals radical G, then those guys. So G must be the gravitational acceleration in inch per second squared. So let me see how much that is. I don't remember it. Gravity acceleration in inch per second squared is going to be how much? 386.09. Okay, 386.09, then times this guy. Alright, so weight 1, 35 times 0.0, the sign doesn't matter by the way, and then plus 55 times 0.02724. Alright, and then you gotta do the same thing in the denominator, but you have to then square these guys. 35.02724 squared. There you go. So let's calculate this. You can use a calculator, or maybe you could use Excel instead. Probably Excel is better. Let me use Excel. Alright. Okay, equals QRT, that's for the radical, 386.09 times 35 times 0.019489 plus 55 times 0.02724 divided by 35 times 0.01489 squared plus 55 times 0.02724 squared. There you go. 124.73. That is gonna be in radian per second. So if I divide it by 2 pi, 2 times pi this will be in hertz, in RPM. Okay, this is radian per second. You divide it by 2 pi. Yeah, it's gonna give me, if I divide by 2 pi, it's gonna give me how many rounds per second? Then I multiply by 60. So what? 1191. This is what I get. Alright, so let's see it. Yeah, I have it slightly off because from this, what book has, because book is using another way, superposition, to do this. We use the answers, but they're close. So, alright, so this is how it works using answers. Now, let's see how we could find this y and y1 and y2 using the other two methods, which is based on superposition, right? So, okay, so let's look at this now. I'm gonna erase this guy. Alright, so let's look at it. So here, we have this problem now. We want to solve it again, find y1 and y2. But this time I'm going to use superposition. So superposition, so I'm not going to explain this Rayleigh equation again because it's just finding y's. So now let's look at how we could use this table, this superposition table, and find y1 and y2. Okay, so here we have this. So for this, for simply supported beam, if your forces you see here is located at distance a from the left bearing going down, then the formation from A to B is gonna be what? FBX divided by 6EIL times x squared plus b squared minus l squared. So this is like the formation from A to B when x is less than a, and for x greater than a, from B to C, this is the formation. Alright, so now let's see how we could do this. Alright, so to do this, you see I have 6 times of EIL is repeated here, so let's calculate that guy. We're going to use it. So let's see. Alright, so see, my tablet sometimes it's not functioning right. so 6 times E I L. I want to calculate it because that's repeated. So 6 times of 30,000 psi times the I, which is 0.04909, and then I have L, which is 31. So let's calculate this guy, see how much that is. That one, let's use the calculator here. So 0.04909 times 31 times 30,000 times 6. Alright, so this is gonna be in, PSI. Okay, so if I want to make this case a PSI, so I should multiply it by 1,000. So now and divide this guy by 1,000,000. Alright, so I get this. Or if I divide another 1,000, it's gonna make it in billions. So like 10 to 9 and is what 0.272739 2739 times to 10 to the 9. The unit, look what it's gonna be. PSI is the I, moment of inertia is inch to the 4th, and you have another inch. So it's gonna be pound divided by inches squared. Okay, so it's gonna be pound inch cubed. Right? So it's gonna be pound inch cubed. Alright, so that's the unit for 6EAIL. Alright, so now, okay, I'm gonna break this problem into two problems. One problem is we have this beam or the shaft. We just have this 35 here, right? So I'm gonna have deformation here at this gear. I'm gonna call it y1 prime due to this weight, and then for this guy I'm gonna call it y2 prime. Okay, so for this problem, what is A? A is gonna be 7. I'm gonna need B. B is gonna be 24. What else I'm gonna need? Okay, so for y1 prime, x is 7. For y2 prime, x is 20. So this is one problem. Another problem is the same beam. Then the force is here, 55. So this time A is 20, B is 11. So deformation at this left gear, I'm going to this time call it y1 double prime. I'm going to call this one y2 double prime. So at this point x equals 7, and on this guy x is again 20. Alright, so we're going to find y1 prime, and we're going to find y1 double prime, and then add them up. Right, if I add them up, it's going to give me y1, and then let me do it here for y2 prime. I gotta do that, and then y2 double prime, and then add them up, and then this is gonna give me y2. Alright, so so for first one, y1 prime what I'm gonna need to use, I'm gonna use, you see these equations I have, I'm gonna need to use this guy, and x equals as I said 7. So let's put numbers. My force is 35, my B is 24, and then that guy 6EIL, that one I have it here, so I'm gonna, this 6EIL is gonna go here, and then in the parentheses, what is x for that one is 7 squared, and then b is what? B is 24 squared, and then you have L, which is 31 squared. Alright, so this is this guy, y1 prime, y1 double prime. For that one, I think it's a good idea for me, see if I can move this guy to the right a little bit. I have more room. Alright, so here we gotta calculate this guy, and then the 4, and then we calculate this one, and then add them up. So y1 double prime is this case. For that one, we can still use this YAB equation, but alright, so let's see. But this time my force is 55. What is my A? Is 20. And then what is L? And then you have L minus X. L is 31 minus 7 divided by 6EL. 6EIL is the same thing. And then you have X. X is what? 7 squared plus A is 20 squared minus 2 times of 31 times X again is 7. Alright, so we gotta calculate these two guys and add them to each other. Let's see, I need to move this further to the right. Okay, so let's calculate these guys. These two guys. So let's go to, alright, I'm gonna need this number. Let's see if I can copy this guy. I copy this fellow to ANSYS. I'm sorry, to Excel. Alright. So this is 6EIL is this guy. Yeah, but if you remember that one, okay, so that one was this times a million. Alright, so this is 6EIL. So 6EIL. Alright, so y1 after calculated 2 times, you know, y1 prime, y1 double prime. Let's do them here. So the first one, this guy, 35 times 24 times 7 squared plus 24 squared minus 31 squared, alright, divided by this guy. Alright, so this is what I got. Yeah, the sign doesn't matter, because you see in this equation I have the force going downward. Okay, so this is y1 prime, y1 double prime. Let's do it. 55 times 20 times, alright, times 21 minus, no, not 21, 31 minus 7 times 7 squared, 20 squared minus 2 times 31 times 7 divided by this guy. Alright, so let's see, this one should come out negative 2. So why it didn't? Let's see everything. 31, 55, 20, 31 minus 7, 7 squared, 20 squared minus 2 times of 31 times 7. Okay, so let me look at here. See if we have the formula right. 55 times 20, 55 times 20 minus times 31 minus x, which is 7, divided by 6 EIL. And then here x is 7 squared, a is 20 squared minus 2 times of 31 times x, which is 7. So look, okay. Yeah, I see what the problem is. Yeah, I see the problem. My bad. Actually, you know what? For at y1 double prime, we still need to use the first equation, yab. That was my bad. I shouldn't have used ybc. I was surprised that it was coming out positive, because that's wrong. So let's modify this. That was my bad. So I still need to use this guy. So 55 times b, let me erase this guy. This part is not right. Yeah, I need to erase this too. Yeah, alright, sorry about that. Okay, 55 times b is 11. Then x is 7. Okay, inside x is 7 squared plus b is 11 squared minus L, which is 31 squared. Yeah, that's gonna change a lot. So let's go here, see what I had here. Alright, so we gotta change this. 55 times 11, then after that times 7, then inside 7 squared, then I have 11 squared, then I have 31 squared. So this one must be 31 squared, and then, alright, this is what I got. Yeah, 55, 11, 7 divided by this, and 7 squared, 11 squared minus 31 squared. Alright, so this is what I got. And then, but the y1 is adding those two guys up. So, adding these guys. Alright, so hopefully I did it right. Yeah, I don't think this is not matching what we had before. So, let's see again. Is there any other mistake here? 55, 55, 55, 11, 7 divided by 6 EIL, then 7 squared, then b is 11 squared, then minus 31 squared. So looks like I have it right. So let's see, 55, 11, 7, and then times 7 squared plus 11 squared minus 31 squared divided by 6 EIL. Yeah, so then you add these two guys, negative 0, 1, 3, 2, 6. This is not right. y1, so y1 is 0.01945. Oh, yeah, so let's see. What is wrong in here? A is 20, B is 11, 55. I'm double checking everything. As here, x is 7, this one x is 20. So, YBC Yeah, y1 double prime 55 times 11 times 7, 6EIL, 7 squared, 11 squared, yeah, 20, 20 and 11, yeah, alright, so 7, 50, 11, 7 squared, 11 squared minus 31, everything looks right. So how about, let me double check this guy. For this one, 35, the summation, they should add up to 0.19. So, let's see which one is wrong. Maybe this one, the first one is wrong. Okay, let's look at that one. 35 times 24, b is 24, x is 7. Oh yeah, okay, I found it. Alright, so let's see. Unfortunately, the problem is here. Yes, 35, 24, this 7 squared, 24 squared, that one is right. So what I have here, I'm going to add it here. I need to, you see, I have another 7 here. That 7 is this x. Alright, so we got to do those two. Alright, so here actually, what I need to do, multiply this by 7 again. There you go. So look, y1 prime, this is 1, 1 prime. This is y1 double prime. When I added them to each other, I got 0.019442, which is very close to here. 0.01944 what I have, right? So very close. Alright, so y1, let me see if I can copy paste this guy here. Yes, where did it go? It went here. No. Let's see if I can paste it here. This is what I got, right? This is superposition, guys. See how you can move this? Yeah. 19.01944. Very close. Alright, so now let's do it again for y2. For y2 again, I need to do y2 prime and y2 double prime and then add them to each other. So y2 prime, at this point, how much is the deformation due to this 35? So you see, for that one, we gotta use this equation because that point is beyond the point of action of that force. So we have to use this guy. So it's 35. What is A? Is 7. Then you have 31 minus, at this point, x is 20, divided by 6EIL, and then I have x is what, 20, plus a, okay, for this one, at this point, a is still the same, 7 squared minus 2 times of 31, and then x at that point is 20. Alright, so we gotta find this, and then y2 double prime, for this guy, when the force is here this time, we gotta use this guy still, this guy. Alright, so how much is the force? Is 55. Your B for the second case is 11. X is 20. 6EIL. And then X is what? This X for that point is 20 squared. The B is 11. And then L is 31 squared. So equals. Alright, so we need to calculate these guys. Alright. So let's come here. First one. 35, then I gotta put 7, and then after that I should put 31 minus 20. Alright, and then you have inside, you have 20 squared, then I have 7 squared, then I have 2 times of 31 times 20. Alright, so this is what I got for this guy, 55, 11, then 20, then inside you have 20 squared, then you have 11 squared minus 31 squared. Okay, 55, 11, 20. Alright, so they add up. You see y, this is now y2 prime, and y2 the double prime. You add them to each other, you get this guy. Oh, I'm sorry. Okay, so I want to move this guy. Yeah. Negative 2027218. Compare with the book. Very close. 2722. 2722 almost. Alright. So, okay, so this is how I found y1, y2 using superposition table. Alright, so now I'm gonna use influence coefficients. You know what your book explains. Basically, that guy is basically superposition, right? But they have just presented them differently. So let's explain that here. So what those guys are, you know what, maybe it's a good idea for me to erase everything. I'm gonna leave these guys. Let's see, I'm gonna need this. Yeah, I'm gonna need this. See, yeah, I'm gonna need this, but I'm gonna use influence coefficient. So let me erase this part. Alright, so we're gonna still need I'm gonna need this 6EIL part, this one. I'm gonna need this. Alright, so this method, let me first explain it. It says, using influence coefficient, it says we have to form a table. If you have two forces, like, we have to form a table of influence coefficients. So if you have, let me come here. If you have two loads and there are, right, two W's or two omegas and then two Y's, you have to form this matrix IJ, you know, 1 and 2, and then what, 1 and 2. You have to form this table or this matrix, and we're gonna find this delta 1 1, delta 1 2, delta 2 1, delta 2 2. We gotta find elements of this matrix. Alright, this matrix. So how do I find these? Using this this figure here. So first let me describe what influence coefficients are by definition. So when I say delta 1 1, it basically means deformation, right, of, okay, deformation at node, or like weight 1 at this point, weight 1, when the load is located, is applied, a unit load is applied to that first point. So this first gear is here, right? So delta 1 1 is influence coefficient, and it's actually the formation or deflection of this point, right, when a unit load is applied to that point. Right? Does it make sense? And then delta 1, 2 is the formation at point 1 again, but this time force, a unit load is applied to node 2, or where the node second load is located. Right? Second. So this is what delta 1, 2 means. First of all, okay, what you need to know is that there is a proof for this in theory of mechanics of material, that delta 1, 2 and delta 2, 1 are going to be equal. So how do I find delta 1, 1? For that you have to come to this figure. So in this figure, look, delta 1, 1. Alright, so delta 1, 1 means at this point, you know how much the formation is. So you come here. So if you want to find delta 1, 1, you see which case is applicable for us? Is this case. So how much is going to be, when I want to use this table, how much is like A? A is 7 for that one. How much is B? B is 24. And then how much is X? At that point, at point 1, X is 7. So we have to use this first line. So how much delta 1, 1 is going to be? So B is 24. And then what is X? X is 7. Divided by 6EIL. Right? And then times 31 squared minus B is 24 squared. Minus, at that point, X is what? X is 7 squared. So influence coefficient delta 1, 1 will be calculated like this. So let's calculate that. As I said, is similar to superposition, but okay, delta 1, 1 is this. 24 times 7 times 31 squared minus 24 squared minus 7 squared. Yeah, I shouldn't have actually deleted 6EIL, but let's say, you know, I'm gonna write it down again here. If it is here, this is gonna be this, right? Delta 1, 1. So delta 1, 1 is this. But let me put 6EIL again here. So what was that? It was 0.2739 times 10 to power 9. Right, is that right? Yeah. Alright, so you see, influence coefficient, first influence coefficient is going to be 0.00002061. Let me see if I got it right with what book has. Yeah, that's right. 2. Alright, so since all of them have 10 to negative 4 repeated, so if I multiply this by 10,000, this is what book has, right? 2.061, right? So this is the influence coefficient 1, delta 1, 1. For delta 2, 2, delta 1, 2 is basically, again, deformation here when the load is applied at 55 at this point. So for that one, again, you see case 1 is applicable, but this time A and B are going to change. It's going to be like this one. So let's do it. So for this guy, first case, right? So what is B? 11. X is still 7. And then divided by 6EIL. And then L is 31 squared minus B is this time 11 squared. And then X is what? Is 7 squared. So this is influence coefficient 1, 2. So let's calculate that. So D1, 2 equals 11 times 7 times 31 squared minus 11 squared minus 7 squared divided by 6EIL, this guy. Alright, so this time I did that calculation again. So again, see what I did. 11 times 7 times 31 squared minus 11 squared minus 7 squared divided by 6EIL. And then again, if I multiply that by 10,000, this is gonna be what mistake I made. Okay, yeah, I shouldn't have done this. I should have done it this way. So this guy times 10,000, so 2.223. Let's go here. 2.224. So I have 2236. So if you round it, you get the same thing. Alright, so this is what? 6 delta 1, 2. You want to find now, so these guys, I found this. You saw that it was matching. And then for this one, you don't need to find it again because they are equal. Delta 1, 2 and delta 2, 1 are equal. Last thing I need to find is delta 2, 2. So delta 2, 2 is when the formation at point 2 when the load is applied at point 2. So for that, this first case is again applicable, but B is this time 11. What is my X? For that, X is 20. So divided by 6EIL. And then what is my L? 31 squared minus B is what? 11 squared. And then minus X is for that point 20 squared. So delta 2, 2 is gonna be, let's find it. Delta 2, 2. 11 times 20 times 31, okay, minus 11 minus 20 squared divided by that guy again, divided by, oh, yeah, I forgot to put that sign, equal sign here. Okay, so divided by this guy. So this is it, and then you have to multiply this guy by 10,000 again. So 3.534. 3.534, this is it, right? Okay, so if you saw how deltas are found, once I have the deltas, then y1. You remember these deltas are calculated based on unit loads. So y1 will be will have two parts, will be delta 1, 1, you remember it was a deformation at point 1 when the unit load is applied at point 1. But we have to boost it up, scale it up, because my load is not unit load, it's 35. So I have to multiply by 35 and then plus, then delta 1, 2, right? Delta 1, 2 was deformation at that point when the unit load was applied to the second point, 55. So again, delta 1, 2 is for unit load. I have to multiply it by 55, then that's going to give me my deformation at point 1 as a result of these two forces together, right? Combined. So you find it like that. And then W22 is going to be, again, delta 21 times 35. And then delta 22 times 55. Right? It's the same reason. Again, delta 21 is the formation of at this point as a result of a unit load at first point. But my load is not unit, so I have to multiply delta 21 by 35 and then add to that delta 22. Again, delta 22 is the deformation at point 2 as a result of a unit load at second point. So delta 22 is for unit load. You have to multiply by 55, add them to each other. If you do that, then you're going to get the same thing as you see here. Yeah, here these two. these guys, right? You're gonna have the formation that I found using superposition and using ANSYS. Alright, so this is how this influence coefficient method works. Again, is nothing but superposition, same thing. It just, what is systematic way of using superposition is very similar thing. Alright, I hope you guys found this useful, this video. That was again to help you guys to find first natural frequency of a shaft when there are lumped like masses, machine elements like gears sitting on it, and we want to find natural frequency based on that. Alright, using Rayleigh equation. Alright, hope you find it useful.